Hello everyone. Hello. Hello Leila, Yudak, Tracy, Tosin, Jesus, TD, Shaza, Sam, Pascal, Pacman, Marionat, John. Just sorry if I pronounce your name wrong. Hello G underscore M. Hello Harp, Giva, Fuz, Nengasi, Esther, Dorin, Ayub, and Sadman, and Nax. So today we're gonna start with this amazing topic. It's called dynamic programming. I had no idea about dynamic programming, but I see it a lot. So today let's see how and what it is and how we can take advantage of it. As always, we're gonna start from the handbook. And by the way, if like you miss some session, you're gonna find them here in this channel, PLD recording. Okay, so introduction. Dynamic programming (DP) is usually used to solve optimization problem. The only way to get better at dynamic programming is to practice. It takes some amount of practice to be able to recognize that a problem can be solved. At least me so I can see the chat. Maybe I do this. Okay. So what that mean? Dynamic programming is usually used to solve optimization problem. The only way to get better is practice, as everything in life. It takes some amount of practice to be able to recognize that a problem can be solved by dynamic program. Okay, so when you practice a lot, you tend to see, okay, I can solve it with dynamic programming, but I still don't know what it is. Technique. Sometimes you don't need to store the whole dynamic program table in memory. The last two value or the last two rows of the matrix will suffice. So we have these problems to solve. We're gonna do like always, try to solve the first one. Convince there is this resources, but we're gonna watch a couple of videos that might help us get to the solution to like solve this. So I had some definition more in details. Dynamic programming is a method for solving complex problems by breaking them down into simpler sub-problems. It is particularly useful for optimization problems, where you are looking for the best solution among a set of possible solutions. Here are more detailed explanation. Breaking down problem, storing sub-problem solution, optimization practice. Solve problem by breaking them down into simpler sub-problems. This is called the divide and conquer approach. Instead of trying to solve a complex problem in one go, you solve a series of simple problems that lead to the solution of complex problem. The second one, storing sub-problem solution. Dynamic programming store the solution to each sub-problem so that each sub-problem is solved only once. Okay, I think when we watch video this gonna be more clear. This is where dynamic programming differ from other divide and conquer method. In other method, the same sub-problem might be solved in multiple times, leading to an inefficient solution. In dynamic programming, once a sub-problem is solved, its solution is stored and reused whenever that sub-problem is encountered again. This is called memoization. Not memorization, but memoization. Okay, that's interesting. Optimization. Dynamic programming is often used for optimization problems. These are problems where there are many possible solutions, but some solutions are better than others. Dynamic programming systematically explore all possible solutions and find the best one. For example, if you're trying to find the shortest path between 2 points, dynamic programming can help. Practice. Dynamic programming is a powerful technique, but it can be difficult to master. It requires practice to recognize when a problem can be solved by using dynamic programming. And to implement a dynamic programming solution, the more problem you solve using DP, the better you will get. Okay, let me share this. If someone want to go to this, there's like more details here. So the technique I'll just read because we're gonna see this in the videos. So there is the top-down technique and there's bottom-up. This is like the two that I saw more commonly. There is this one, optimal substructure, overlapping subproblem, DP on tree, state transition. But this is, I think, the main one, top-down, memoization, and bottom-up, tabulation. Here's the link. Okay, so now let's jump. So it's okay if you still confused or you just join. We still have no idea on dynamic programming yet. Let's hope this video gonna put us more on track, and let's go. First, I think to hear audio, I need to change screen. So stream only the window, right? Where is it? This one. Okay. Let me add the more volume. Okay.
What's up, guys? Welcome to another video of the course.
You can hear audio. You can write in chat or confirm in mic.
Dynamic programming for beginners. This is part 11, and today I would like to talk about the difference between top-down and bottom-up approach.
Yes, Shaza. Can you repeat? I didn't hear you. Shaza, did you say something?
I think the voice is too low of the video.
Oh, maybe you can control the stream volume. I think it's at the max. I can paste it in chat just in case someone will like try to watch the video directly from the chat or the Chrome. Okay, I'm gonna play. Let's go.
When it comes to solving dynamic programming problems, as I mentioned before, the goal of this course is to explain the topic as simple as possible, in the fashion of explain like I'm 5. So, in order to explain both top-down and bottom-up approaches, I would like to step away from the computer science for a moment and answer the general questions first. What is top-down? What is bottom-up? What are these terms at all? So, top-down and bottom-up are both strategies of information processing. These strategies are used in a variety of fields such as management, psychology, manufacturing, as well as in computer science. For a second, let's dive into the world of psychology, specifically the world of perception. What is perception? Perception is basically a process of organization and interpreting sensory information.
Everything's good, right? Everyone can hear, everyone following. Okay, let's keep going. Try to understand what he's trying to say, and the more we like, if someone have question, I can pause the video, we can discuss it, or I can go back a few seconds if you want to catch up. And let's go back a few seconds.
Let's dive into the world of psychology, specifically the world of perception. What is perception? Perception is basically a process of organization and interpreting sensory information. There are two basic approaches to understanding how the perception takes place. One of this is known as bottom-up processing, and the other is known as top-down processing. In psychology, bottom-up processing refers to processing information as it's coming in, sort of like in real time. Top-down processing is when we form our perceptions starting with a larger idea before working our way toward more detailed information. In other words, top-down processing happens when we work from the big picture to the tiny details. Let's take a look at the difference between top-down and bottom-up processing. If I were to draw an obscure shape, something like this, and ask you a question, what is this? By using bottom-up processing, you would probably tell me that this is letter B. But then, if I were to add some context to it, this is no longer letter B, but 13, right? Number 13. Why? Because you have some context and you're solving essentially sub-problems. And this is a top-down approach, top-down processing. You're solving sub-problem, this sub-problem, and that sub-problem, and then you can answer the general question that this is 13 and not letter B. If I were to add even more context to it, again, you're using top-down processing. You're looking at A, you're looking at C, and the result, you can tell me that this is a letter B, right? So this is the difference between top-down and bottom-up processing. The other example would be if I were to give you a random text, a sheet of text, right? And I would ask you to tell me what this text is about. There are two ways how you could read the text, right? One way is to read it from the top to bottom, like all of us read regular text. This is one approach. And the other approach is to start reading somewhere in the middle, then at the end, and then at the beginning. This would be a bottom-up processing. It's basically the other way to read a text. So this is the difference again. This is what top-down and bottom-up processing when it comes to perception. Now let's get back to computer science. In the software development process, the top-down and bottom-up approaches play a key role. Top-down approach is based on planning and a complete understanding of the system. This strategy is implemented by attaching the stops in place of the module, and then all the individual subcomponents are being implemented later. Top-down approach is more suitable when the software solution needs to be designed from scratch and very specific details are unknown. Bottom-up approach works in the exact opposite way. You start by taking small components and assembling them into a desired system. So bottom-up strategy is more suitable when a system needs to be created from some existing components. Now, what about dynamic programming? When it comes to solving combinatorial and optimization problems, we can use either top-down or bottom-up approach. Let's talk about the top-down dynamic programming first. We are going to review the popular Fibonacci function. When it comes to Fibonacci, one way to solve it is to use recursion. And when it comes to recursion, there is a recurrence relation, right? So for Fibonacci, it's f of n equals f of n minus 1 plus f of n minus 2. Very simple and very popular. So let's take a look at the recursion tree when we solve Fibonacci of 4. So to solve Fibonacci of 4, we would need to find Fibonacci of 3 and Fibonacci of 2. To find Fibonacci of 3, we would need to find Fibonacci of 2 and Fibonacci of 1. To find Fibonacci of 2, we would need to find Fibonacci of 1 and Fibonacci of 0. To find Fibonacci of 2 here, we would need to find Fibonacci of 1 and Fibonacci of 0. So this is how a regular recursion tree for the Fibonacci of 4 looks like, right? What's the problem with this? The problem is that the runtime complexity is exponential. So big O of 2 to the power of n. And there is a way to optimize it. How? we can use one way to optimize it is to use top-down dynamic programming. What does it mean? Well, it means that we want to save we want to avoid calling some functions. So in this recursion tree, for instance, we call f of 2 twice, and then f of 1 is also called twice, right? So if we store the values of this function calls to a hash table or maybe an array, then we could reuse those values later. This is called memoization. Memoization. And we've talked about that at some point.
Okay, I wanna repeat these parts. I think it's need more focus.
And there is a way to optimize it. How? We can use one way to optimize it is to use top-down dynamic programming. What does it mean? Well, it means that we want to save we want to avoid calling some functions. So in this recursion tree, for instance, we call f of 2 twice, and then f of 1 is also called twice, right? So if we store the values of this function calls to a hash table or maybe an array, then we could reuse those values later. This is called memoization. Memoization. And we've talked about that at some point. So memoization plus recursion, that's what top-down dynamic programming is. So if we apply memoization here, then we would not have to go this whole route. So this subtree essentially disappears. And then this f of 1 call disappears as well. And now, as you can see, the runtime complexity becomes O of n. And that's pretty good, right? Now, what's about bottom-up dynamic programming? So, they say that bottom-up dynamic programming is the real dynamic programming, and then the top-down DP is just a recursion plus memoization, recursion plus caching. So with top-down dynamic programming, we say, okay, so I want to find f of 4. In order to find f of 4, I need to find f of 3. To find f of 3, I need to find f of 2. To find f of 2, I need to find f of 1. With bottom-up dynamic programming, it's the opposite, right? So we say, okay, so I need to find f of 4. And we could even change the problem statement a little bit. Instead of finding f of 4 specifically, we could say, well, let's find all the Fibonacci numbers for all the numbers up to 4. So we already know what f of 1 is. It's a base case, right? So we could say, well, knowing f of 1, I could find f of 2. And knowing f of 2, I could find f of 3. Knowing f of 3, we can find f of 4. So this is bottom-up dynamic programming. When we solve problems with bottom-up, we essentially solve all the sub-problems. When it comes to top-down, we only solve the ones that we need specifically. So this is a minor difference between the two. Bottom-up dynamic programming is also called tabulation. Sometimes you can hear this term as well. And the reason why it's called tabulation is because we use a table, and when I say a table, I simply mean an array, in order to store the results of sub-problems. So for this specific problem, we would create an array of size n, or maybe n plus 1, and f of 1, we know that, that f of 1 is 1, f of 2 is also 1, or we could start from 0, right? So f of 0 is 0, f of 1 is 1, f of 2 is 1 as well. So we essentially store the results in an array, regular array, right? Then f of 3 is the sum of the previous two, so it's 2. This guy, f of 4, is essentially 3, right? So that's how the bottom-up DP works. We store the results to sub-problems in this table, in this array, and then the major difference is that when we use bottom-up approach, we always use iteration. it's always about iterating over this array. So it means that we are not, there is no way that we will ever get a stack overflow, because with top-down dynamic programming, if the recursion tree is too deep, it's possible that we can get the stack overflow error. Okay, so what else? So the other thing about bottom-up approach is the fact that there are two ways to calculate subproblems. So one way is called forward dynamic programming. It means that we know several values, several results to, in this case, 3 subproblems, and by using these values we can calculate the result of the next sort of like subproblem, right? So this one is unknown, this one is unknown, and this is a forward DP. And there's also backward DP. When it comes to backward, it means that we know the result of only one subproblem, and then we can contribute to other subproblems and find the result of those. So these 3 are unknown. And I'm going to show both of these ideas in code. And let's actually take a look at code. Let's finish the whiteboarding session. And I think by looking at actual code will help us to sort of like better understand and better digest the ideas about top-down and bottom-up dynamic programming. All right, so I've got my editor. I've created empty functions here that we're going to implement. And the first one is a regular recursion. So if n equals to 0, we simply return 0. These are base cases, right? And then if it's less than or equals to 2, we return 1. Otherwise, we just call ourselves with n-1 plus Fibonacci of n-2. So this approach is not optimal, right? It's exponential runtime complexity, which is too slow, and we want to optimize it. We can use top-down dynamic programming by adding memoization. So this one is just recursion, and that one is recursion plus memoization. So let's create our...
Okay, so this not dynamic program, but regular recursion. Okay, so the first solution is just like a brute force. The second one, this is top-down dynamic program, aka recursion plus memoization. So let's say this memoization is a way to not go through the same path. So to not go through the same path again. For example, when he design this. So for example, if here we split F2, F3. Now if I go to the left path, I go to F3 and then I go F2. So if I process F2, when I go again to the right path, I will go process F2 again. So this is like just a waste of time because it's gonna give us the same results. So with the memoization, I can avoid that. So if I process F2, I save it. I save the value of F2. When I go to right and I find F2, I don't process it. I just use the value that I save. I hope that was make it a bit clear. Okay, now this is a top-down dynamic program, aka recursion and memoization. So this is gonna be both recursion.
Otherwise, we just
this one gonna skip the path that we did already process.
Call ourselves with n-1 plus Fibonacci of n-2. So this approach is not optimal, right? It's exponential runtime complexity, which is too slow, and we want to optimize it. We can use top-down dynamic programming by adding memoization. So this one is just recursion, and that one is recursion plus memoization. So let's create our hash table that we'll use to store the results of subproblems. And then I'm going to create a helper function which will accept n and the hash table. Now let's define it. It's a helper, and then memo is a hash table, and then we return integer. Now I'm going to handle base cases first, and then if the subproblem has already been calculated, then we simply want to return its value, right? We don't want to recalculate it. So we can say,
Okay, so this is the key right here. It's same recursion. It just, if it was already processed, I guess he did a map here as a way to memorize. He just gonna return the value of it.
say if memo of
Wait, can you repeat, Shaza?
The function of flip top down. Can you please explain it? I can't understand what is he doing in flip top down.
Okay, so
Yes, one. Yeah.
okay, so fib top down, I guess it's like here where we gonna like memorize the like to not like process the same numbers. For example, a fib of 2, I need to check maybe if I have I'm not sure how he gonna use it here, but if we see fib top down, you give it in, to return int, and it's go to memo. I don't know if this C++ or Java. Oh, Go. This is Go. Okay.
Yes, go. Yeah.
So it's a map, and
Yes.
he declare a key. I guess a key with like 2. Maybe this mean it's gonna be a value int type. So and then he call recursion, right? Oh no, then he return this. So he called this, he give it n and the memo, and the memo is gonna be this. So basically, okay, so he gonna do a check here. He gonna do like, if this number exists in memo, just go to the memo and go to that key and take the value, return it.
Okay.
But if it wasn't in that hash map, then do this right here, this fib in -1, fib in, So basically, this is the start of the function dp top down, and it creates a hash table, and each like points, for example here. So each point here, I'm gonna have them in hash table on the value. So f3, I'm gonna add it to the hash table. I'm gonna write 3, and the value is gonna be the return of this, and 2 and 1. So when I'm going in recursion, before I call recursion, I check, do I have that? For example, I reach here 2. I save it, the return in hash table. When my recursion go to this f2 right here, when he go to this site, when he gonna do f2, before I do it, he gonna check, he gonna find it already in the hash table, so it will not process this, like it's not gonna process the recursion. It's gonna just take the value and return it to the f4.
That's sweet.
calculated, then we simply want to return its value, right? We don't want to recalculate it. So we can say if it's a helper. Now I'm going to handle base cases first, and then if the subproblem has already been calculated, then we simply want to return its value, right? We don't want to recalculate it. So we can say if memo of n has already been calculated, then simply return its value. Otherwise, calculate it and store it. So otherwise, memo of n equals fib top down helper n minus 1 memo plus fib top down helper n minus 2 memo. And then finally, we can return the result.
Yeah, I guess
so this is
the same, what I understand. he check here if that key exists, or like that value of that key exists. I don't know how this work. So maybe if it doesn't exist, it's gonna return. It's gonna be 0. Oh, maybe he gonna put them all 0 first. I guess it doesn't matter, but he check here if that value exists in hash table. If it exists, he return it. If it doesn't exist, this means it's not gonna enter this parts. It's gonna go directly here. It's gonna do n-1, n-2, same as we did in the normal recursion, but this time we also pass the hash table, so each recursion gonna have access for the hash table, so it can check if its value already there or not, and then return the hash table. It's gonna return it to where? No, it's gonna return the n. I know. Don't know what that is. Oh yeah. So because this hash table is gonna have a Fibonacci of all the numbers that we process, and when we call this fib top down, we call, for example, give me Fibonacci n for example 5. So I'm gonna go to the hash table and I'm gonna go to key 5 and I'm gonna return it. So basically it's gonna have in this hash table gonna be Fibonacci of 0, 1, 2, 3, 4, 5.
Top-down dynamic programming, recursion plus memoization. Now,
Please, if you have questions, something confusing, we can just ask. This is a bit advanced, I think, at least for me. So we can get help with the ChatGPT or someone here more expert in this field. He can help us.
Now, let's do bottom-up dynamic programming. So let's solve the base cases first, and then after that, we can create a table which we'll use for...
Okay, so this one, the second technique for dynamic programming. The first one that we saw, it was top-down, that we start from the top, then we go down. And we need the help of some place to memorize the values. This one we're gonna start from the bottom and then we're gonna go to the top.
Solutions to our sub-problems, and it's going to be of size n+1. Then we can specify base cases dp of 0 equals to 0, dp of 1 equals to 1. And then we can solve sub-problems starting from the second sub-problem all the way up to the last sub-problem.
Why did this? Maybe because Fibonacci of number 0 is 0 and Fibonacci of number 1 is 1?
Yeah, those are the very beginning, the building blocks of your Fibonacci.
Okay. I know what this make mean. Maybe create a list of integer. Oh, make is a function maybe.
An array.
Something.
And we can apply the transition function dp of I equals dp of I minus 1 plus dp of I minus 2. We've done that many times, right? And then...
Okay, so the same recursion here.
The result is
No,
dp
this is not
of
recursion.
n.
This is...
And as you can see, this is...
Okay,
No,
so
it's
this
not
is
recursion.
Fibonacci, yeah. Okay, so e minus 1, a plus a minus 2.
a forward dynamic programming. So by knowing f of I minus 1 and...
If I get e. So if a minus 1, e minus 2, it gives me e.
I minus 2, we can find dp of I over here, right? Now let's take a look at
Okay, wait. So this is bottom up. Forward, there's backward, but let's say he returned dpn. Okay, so for e2, so it starts from 2 and then the last one you said, yeah, Fibonacci number. Okay, so the last element in the array, n.
Because we want the Fibonacci of the last number, the n number.
Oh,
That's
so
why
the
he
index.
returned the dp of n.
Okay, so they match the index. So Fibonacci of number 5 is gonna be in the index 5.
Exactly.
That's cool. Okay. Okay, I see it. So this is simple actually. So 4, 2, so he's gonna jump 2 step because we already fill in line 52 and 53. He gonna keep looping until e equal the number we're looking for. So as long as not equal, he gonna keep looping, and each and or new place in array, he gonna put dp of the previous number by -1 plus the dp of the previous number by 2 step backward. Okay, and he gonna keep looping. But what if we didn't find the target? I mean, if the target is 5, we're gonna keep looping until we find 5, right? For example, 5, then we already have 0 on the 1, so we're gonna keep looping until we find it. So this is forward. I'm curious how it is
Bottom-up
backward.
dynamic programming. It's the opposite of
I
forward.
guess it's backward because maybe you are getting it from, instead of starting from the top one, you start from 5 and call back function till you get to 0. I think that's the top down. Then the down up, you pick random numbers and you call back the function. I think that's the difference, because you are doing sub problems. So if instead of starting from 0, maybe start from 4, you call it back and you move over to 2. So you are solving soft problems before you get the bigger picture. I think so.
Okay. Let me just zoom a bit. 1 second. Okay, maybe if I did like this. Does this look better?
Yeah, you can see a little better.
Okay. Let's keep going.
Dynamic programming. So we will do the same. First, we'll specify base cases. Then I'm going to...
Okay, wait, someone asked like we didn't give it a end. The parameter of function is n. N int mean we want the target. So because there is no end, I think, because we are looking for 5. So we're gonna keep looping until we find 5. Did you get it? So can you see my escalator?
He thinks that the function just looping in the Fibonacci list. He didn't see the target because function has the parameter of the target, like the n number.
Yeah, I think it's have n because we're looking for n right there. In so 2, 3, 4. So we start this one. It's gonna be 0, 1. Fibonacci of 0, 0. 1 is 1. Then we keep looping. We keep looping from 2. So 2. Let me write it like this. Then when we go here, we do this one. What was the equation? E minus 1 minus 2. So
it's 1. It's 1.
1. Is this 1? Wait.
Yes. Yeah,
E,
that's
so
1.
like 2.
It's 1.
2 minus. So 1. okay, let's just say 2 minus this plus this, so it's gonna give 1, right? Then we're gonna move here. Then
It's
again,
2.
okay, 2. So
2,
it's
3.
3. 2, 3 what?
3, 5, I
5.
guess.
So it's e minus 1 plus e plus 1.
No, e
That's
minus
minus
2.
2.
Two.
A minus
Okay,
1
my
plus
bad.
E minus 2, yeah, exactly.
Minus 2. Okay, so we move here again, a
It's-
minus 1, which is this one,
It's like
plus
it's
this
like
one.
adding the previous with the previous of the previous.
Again here, minus this one, plus again minus this one. Again here, minus this one, plus minus this one, which is 5 minus this. Now we can keep going, like there's no one can stop us. We can keep looping here until like 1 million number, right? But we are looking for 5, so that's why in the if function we said equal or less than 5. So as long as it not, so as long it, wait, is it equal? I think like that. Oh god, I can't focus.
You're correct from the beginning. You're correct.
Okay, so like this. So it's as long it is less than 5, I'm gonna keep looping. So even if when it's gonna reach 5, I'm gonna keep looping the last loop. I hope it's clear. A72. Okay, let's
Yeah,
keep
it
going.
makes sense for this example.
Copy this part, and instead of n plus 1, we'll do n plus 2. And the reason why is because we will contribute to 2 subproblems. So let me show it to you. While I less than n, I plus plus, so dp of I is already calculated here, right? So dp of 1 is already calculated. And by knowing that, by knowing this value, we can calculate I plus 1 and I plus 2, right? So we can say I plus 1, we contribute to it the solution of dp of I. And then dp of I plus 2 can be solved like so, right? So here dp of I is already solved, and we can use it to solve other subproblems. So as you can see, dp of I is known, it's already known, and then we use it to find I plus 2 and I plus 1. And then finally, at the end, we can return dp of n. Same thing.
Okay, I'm a bit not following here. If someone understands, you can like try to explain, or we can just go line by line, see what's happening here. So so here the difference is starts plus 2. Wait, is the other one is not plus 2, right? So this one plus 1. I'm not sure what this mean. Make. Okay, we don't know what make, but he did say something here about. Let me repeat that part when he said change minus 1 to minus 2.
Copy this part, and instead of n plus 1, we'll do n plus 2.
Why?
And the reason why is because we will contribute to 2 subproblems.
Because there's 2 subproblems. Okay, because there is e plus 2, e plus 1. So basically we need to have two empty index, one for this, one for this, I think.
So let me show it to you. While I less than n, I plus plus, so
a plus 1, so he gonna start from 1, a minus n, a plus plus. Okay, he needs to start from 1 because we have e plus 1 here.
Oh.
Okay,
dp of I is already calculated here, right?
dp of I is already calculated. Yes, because it's 1. dp of 1 is 1.
So dp of 1 is already calculated. And by knowing that, by knowing this value, we can calculate I plus 1 and I plus 2.
By knowing this value, we can calculate I plus 1, I plus 2. Okay.
Right, so we can say I plus 1, we contribute to it the solution of dp of I. And then
Oh. So this e plus 1, which in this case gonna be 2, right? Because a is 1. Now the e plus 1, it's gonna be 0 plus dp.
Yeah, exactly.
So it's gonna be
What
1.
he's doing,
So it's
he
gonna
used
be
the
1.
previous one to get the next one. Exactly.
So yeah, so somehow this line is gonna add this to this. So it's gonna add this on this. I'm just wondering if this have the value by default 0. Oh, I think so. Let's see. Let's see. You know what? Let's look this make command. What is gonna do? I guess we are programmers, right? So sometimes you need to explore new languages. Let's see. ChatGPT, please help us.
It's like creating.
I checked it and it's like you wanted
Yes.
to make an array.
So it like generates array.
Yes. Or a map, a collection. You can check it again.
Is it static or dynamic? Is it a static array?
It depends on what you feed it. So it has arguments on the length.
No, they make. Is it creating a static or?
I think it's
maybe I
dynamic.
fit. dp equal.
It's dynamic.
What this do?
It's in Go.
So creates slice name dp with the length of n plus 2. So int, if we are looking for 5, n plus 2 is gonna be 7, right? If we are looking for
Yes,
but why
but
did add? Okay, and
the return is not specified.
okay, and capacity of n plus 2, the elements of the slice are of type int. This is common pattern dynamic programming to create an array or slice in Go to store the results of sub problems. Make this create a new slice integer with the length of n plus 2 and the capacity of n plus 2. The elements of slice are initially set to their 0. Okay, that's what was confusing me. Because when he does this, when he did plus equal, so I thought, is it there is 0? So by default it have 0. So I can just add to its number. It's gonna just set it for int type dp. This declare a new variable dp and assign the new created slice to it. This operator is used for short variable declaration in Go, and it infer the type of the variable from the type of the expression on the right hand side. Okay, so we understand it now. Now my question, why he did +2, someone said for result. So now this array, the length of it is what? 0, 5, right? The length of this array is 5. Why when
No, I think it's 6.
it's 6? Yes, you're right, 6. So the other one, we have one extra place. We need to know why, right? Because we did n plus 2, not plus 1. So this extra is gonna be the result because we are working backward. Because when we were looking forward,
Let's try the pseudocode of the code.
yeah, but we didn't finish yet the code. Let's see what he's gonna write. Or we finish it,
of
but
I plus
going line by line.
You know, it's always better for the for it to be more than less. Anyway, just continue.
Yeah, but now we know
+2.
what this line here does, right? So the 4 is starting from 1, and then he go to this. He add this value to this plus to give you 1, because this is have initial value 0. Now he did that. Then what he's gonna do? He's gonna do dp e plus 2. So in one loop, he's changing 2 indexes or 2 places in array.
can be solved like so, right? So here dp of I is already solved, and we can use it to solve other sub-problems. So as you can see, dp of I is known, it's already known, and then we use it to find I plus 2 and I plus 1. And then
Okay, so this e plus 2, he did add to it dpi. So where is e plus 2 here? E, so this is e
It's
plus 1. It's gonna be this plus 1 plus 2. Now what he did put on it, so this one was 0. Oh no, it wasn't 0. It was n plus 2. Oh, so the array of dp, it was like this 0, because it doesn't make sense if we add 1 here, right?
It was 0 and 1. That's what it was.
No. Look, Nux. It's normal because he will get on it and the next loop.
Oh,
if you see
smart.
one place,
Yeah, because
you know what I mean.
yes, because
I mean.
yeah, because we in this loop we are still here, right? We are still what?
Yes.
The heck? Wait, so we are still here. So we are still here, and then
Yes.
we add this. Let's Okay, this is really exciting to understand.
That's what I said before.
I'm sorry, I am slow a bit, so you need to say it many times. Okay, so
It's okay.
So we are here, right? And then this is 0, but we add the value of this one, and then we add it in same time to this. Okay, now we're gonna loop again. Oh my god, I have so much stuff here. Okay, remove this stuff. No wonder I can't focus. Okay, so in the next loop, this also gonna jump, right? It's gonna jump like this. Right there. Okay, let me go back. So this also gonna jump here, right?
The pointer will point to 3 and 4, the next loop.
So this one gonna become 2, right? And this gonna become 1, right?
Yes.
Exactly. No, this will hold the previous one.
The previous is 1.
Yeah, yeah, yeah.
So 1 plus 1 is 2, and this is half 0 because we didn't reach
No.
it we didn't reach it yet. So it become 1.
Yes.
Now we go to the second loop. Now this also gonna jump, so the value of 2 is gonna add to 1.
It's
What's
3.
gonna be? It's gonna become 3. And this, because it's half 0,
Two.
it's gonna become 1. And then
No, it's 2. It's 2 because the current,
sorry,
the
2,
current
2,
is
2.
2.
Yeah, I forgot. 2. Because here we have 2. Then we're gonna loop again. Then this 3 here, it's gonna add to this 2 right here. What's gonna happen? It's gonna be 5.
5.
Wow, look, they are saying genius.
So that's what he's using a previous solution to solve the subsequent solution problems. That's what he's doing, and that's smart anyway.
It's brilliant.
Yeah.
Finally, at the end, we can
So how we can separate between them? This is backward, this is front, like forward. Other one is forward. I know why this is called backward. We are still going from this direction.
I think because we predict the next one, then we go to the next. But forward, we just take the last one. Know what I mean? We take the previous.
Yeah, yeah, that's
Now we predict
exactly.
the next.
Okay, I'm gonna act like I understand you. Then later I'm gonna try to understand it. Let's keep going. I see. Okay.
return dp of n. Same thing. Now let's run the tests and see if things work correctly. Okay, so it looks like everything is good. We don't have any errors.
Okay, so
you don't
there's
have
nothing
down
here.
recursion here, so it's easier to reason about the code for actually two things. So the first thing is that the code for bottom-up approach is way easier to read. You don't have recursion here, so it's easier to reason about runtime and space complexities.
Okay. Okay, now that we have the bottom code forward, can you explain again? Maybe
I said that in the forward we take the previous ones, like we are in E, like
E minus 1.
let's
Oh,
like,
okay, okay.
know what I mean?
Yes. Okay, now I see it. So because here we go to minus
To
1.
previous.
Yeah, when we are moving through this. Each time we move, we check the previous numbers. But this time we are moving, but we are like adding in the other side. So
Yes, that's
that
what
is
I was saying.
that is difference. So this one is moving forward, and this one kinda backward. Okay, I see the difference now. Please, if someone have question, don't be shy. Go ahead. We try to understand this. We still have, I think, 2 videos to watch. Okay. Someone write something in the chat. What was that? Okay, this is a code. Fibonacci top down. Oh, it's like a trace for it. The memorization help avoid redundant calculation, significantly improving the efficiency of. Okay, so we jump the one that we already calculate. This one with Python is very short. Okay, let's see this video right here. It will make it more clear for us. Let's keep going. If someone have question, please go ahead.
Imagine we start with the numbers 0 and 1, and we take these two numbers and sum them together, for 0 plus 1 is equal to 1, and add this to the sequence. Then we take these two numbers and add them together, for 2, and then we keep going. 1 plus 2 is equal to 3, and then 2 plus 3 is equal to 5. Then 3 plus 5 is equal to 8, and so on. This sequence can be represented using the following functions, and it's known as the Fibonacci sequence. It's commonly used as an introductory problem for showing recursion and dynamic programming. In code, we'll have a base case for n is less than or equal to 1. We will return n, either 0 or 1. But the magic really happens in the other branch, where the return value is going to be the sum of the two previous values in the sequence, and we retrieve these through recursion, that is, through the function calling itself. But this function has a significant performance problem. To see this, let's first visualize the function calls as a tree. Starting from the root of the tree at n, the left path is the previous value and the right the value before it. Each side of the tree will grow until we reach leaf nodes at one of those base cases of 0 or 1. Due to the recursive nature of the function, the worst case runtime at each step of the fib function is going to be equal to the runtime of running it twice with an input of 1 or 2 less, and a constant factor that's going to account for the less than check and the addition. This formula might look familiar. It's actually the Fibonacci function again. The bad news, however, is that this grows exponentially. Even on modern hardware, calculating the Fibonacci sequence in this way, using relatively small values for n, it's going to be infeasibly slow. Looking back at
Okay, here's this part again. So the normal recursion, we go all possibility. So okay, I'm still trying to understand. Okay, Tosan, if you have some question, please go ahead. I will try to. Okay, maybe maybe you can ask question even in chat. Okay, someone.
Do you see the repetition in the nuts?
Okay, can you repeat, Nangasi?
Do you see the repetition there in calculation?
Yeah, n minus 2 here, and we have it also in the right side, n minus 2.
This case it's not by memoization.
So this one is just.
There is no.
So I will try to summarize for Tosan and Leila, like what I understand so far. Someone may add to it. So why we go to better to use dynamic programming? Because sometimes you can optimize the time complexity and space. So like you're gonna use less memory and shorter time. How you can do that, as we saw in this Fibonacci problem, sometimes your code is solving a big problem, right? Now this big problem, you can always split it to small problems, right? Now when you split it to small problems, you're gonna notice that some small problems are the same process and same value. So it doesn't make sense why we keep doing it twice or 3 times if it is the same parameters and same return. So the idea come, okay, if these small problems is the same, let's not process it. This way we're gonna save that CPU or RAM. I'm gonna save energy, and I will have already, for example, that value saved in some memory, right? So if I need to process that sub problem, and I check if I have this problem processed before. If it's processed before, I just take the return. So this is kind of what I understand so far from dynamic programming. Let me know if it's clear, Leila and Tosin or anyone else. Okay, let's keep going. Ningasi, you were gonna say something, right?
Yeah, I was just gonna say, if you think about the recursion without memorization or memoization, it's repeated effort, right? And then as well, if you think about how the program is stored in memory as well, it would mean that this space again needs to be taken up until, of course, all these branches have, reached their base cases, and then only then can you start freeing up the memory. So if you have an extremely large number, that would require you to have an extremely large amount of memory, and it'll also be inefficient in that you've already counted I mean, you already calculated some of these things before, so you just be duplicating some of your effort as well. So with the top-down and the bottom-up with dynamic programming, you're removing the inefficiencies of having to, one, calculate something over again, and of course the space complexity as well. You're decreasing that by not having to do or store anything more than you have to get to the solution. So it's a way more efficient way of solving a problem by breaking it down and not repeating your efforts.
Please, anyone have a question or something?
I have a question. Please, I want to know if I'm correct.
Can you repeat, please?
I want to know if I'm correct. From what we are seeing in this image, we see that at the left-hand side and the right-hand side, we have n minus 2. We also have n minus 3. We also have n minus 4. Does it mean that if we use memoization and n minus 2 is being calculated for the left-hand side, so by the time we go to the right-hand side, we won't have to calculate again for n minus 2 because we have stored it somewhere. Is that true?
Yeah.
Okay, so I see.
Any more question? Okay, let's get going.
With the tree, we can see why. When you inspect the descendant nodes in each of these branches, you'll see a lot of duplication. For example, n-2 appears in both the left and the right branches, but entire subtrees are also duplicated. As the value for n grows, the size of the duplicated subtrees will also grow, and you'll start to see the same duplication in more and more branches in the tree. This is the cause of the performance problems with the recursive Fibonacci solution, and dynamic programming provides us with two approaches to try to fix this. Let's first try optimizing this tree a bit. To avoid this problem, we might say that if we ever encounter a value we've seen before, we shouldn't try to explore any further, and we can just return the value that we saw before. That would look something like this. Even with a small value for n, you can see
this is make it look perfect. So here, we already did it.
that this has greatly reduced the effort required, and it's basically entirely removed that rightmost branch. In code, this might look something like this, using a caching decorator from Python. This method is called top-down dynamic programming, and you might sometimes see it called memoization. That's memoization rather than memorization, and it's a type of caching. It's called top-down dynamic programming because we start at the root of the tree, the highest number, n, and we work our way down the tree to the smaller subproblems. Without access to a caching decorator, this would be implemented manually with a hash map. If the value for n is in the hash map, then we can return that value in short circuit. Otherwise, we run the fib function as normal and store its value for next time. Imagine we now flatten out this tree from smallest to largest element. This is starting to look a bit more like the visualization of the Fibonacci sequence that we saw at the start. And we know we can calculate it in this way, by adding adjacent elements together and working towards a target. This approach is called bottom-up dynamic programming, as it starts from the base cases and lower.
Okay, so this one is bottom up. Okay, let's go back to the top.
This is starting to imagine we now flatten out this tree from smallest to largest element.
So this one we start from n. That way it's top to down. Okay. So it's gonna be recursive here. So we start from n, then n call n minus 1, then n minus 1 call n minus 2, and n minus 3, n minus 2 call 2 recursive, n minus 3, n minus 4. Then when they finish, this is the base. So n minus 3 and minus 4 are the base for our recursion. When they are returned, it returns to n minus 2, it returns to n minus 1, then we find out n. Now in the bottom up,
smallest to largest element. This is starting to look.
It's gonna be, we start from n minus 4. So we start from the bottom, then we calculate n minus 3, n minus 2, until we find n.
A bit more like the visualization of the Fibonacci sequence that we saw at the start. And we know we can calculate it in this way, by adding adjacent elements together and working towards a target. This approach is called bottom-up dynamic programming, as it starts from the base cases and lower values of n and works towards the larger subproblems and the target. You might sometimes see this approach called tabulation, as the process is a bit like filling in a table. The code looks a bit like this. You create a table, which is often an array in code, and add your base cases.
Okay, so table, append 0 and 1. Okay, this is kind of the same code we saw in Go. So for E in range, so it starts from 2, like we said before, and you just append that's -1, -2, so it's same the code.
You can then loop over the input values in their dependency order and sequentially calculate the solution to the gradually increasing subproblems. The overall solution for the Fibonacci sequence is then the last value in the table. In some other problems, you may need to take a max over the table, and I've got another video giving you some pointers on how you can build the intuition around why some problems require that. An important thing to notice about this code is that there is no recursion implemented in it. There is logically recursion, but instead of recursively calling a function in code, we are referring to previous entries in the table and computing those entries iteratively. Sometimes, in certain courses, bottom-up dynamic programming might simply be called dynamic programming, and you'll be expected to use it. In other courses, you might need to know both and be able to solve problems using either. Either way, it's good to understand the pros and cons of each approach. One of the major pros of the bottom-up approach is that it's easier to analyze the runtime. You don't need to go and solve a recurrence relation and think about the size of the subproblems. Instead, the analysis is usually reduced to counting loops and their level of nesting. Similarly, while the sets used with memoization have an O1 average runtime for their lookups, in the worst case there could be collisions in the set, which regresses the lookup runtime to O of n. In an algorithms class, this can be a bit of a trap, and it's avoided entirely with bottom-up dynamic programming. At the CPU level, the tight loops of the bottom-up approach perform better than recursion, as they avoid all of the overhead of recursive calls on the stack. Finally, with large values of n, the top-down approach might run into stack overflow issues if the depth of the recursion gets too large. But top-down dynamic programming has some pros too.
Okay, so by doing bottom to up, we avoid the hash map, data structure, and in worst case. Tight loops perform better than recursion, avoid stack overflow with large input. Okay.
So the recursion gets too large. But top-down dynamic programming has some pros too. The first is that for most people, it's generally more intuitive to think about a problem in terms of smaller subproblems, especially if you've come across recursion before. In some other problems, it's also not so easy to figure out the dependency order that you need to calculate the subproblems in. In top-down dynamic programming, this is handled automatically due to the recursive dispatch, where it calls dependencies on demand. If you already have a recursive solution, then memoization can be trivially added. As we saw earlier, it's just a single line decorator in Python. Converting to bottom-up dynamic programming, on the other hand, it's not just an optimization. It's going to require rethinking the problem and probably a rewrite of the code. For certain problems, unlike in the Fibonacci sequence, the top-down approach might be able to come to a solution by only visiting a small subset of the state space. You can see this with a knapsack problem, for example. But with the bottom-up approach, all preceding subproblems instead need to get blindly solved, irrespective of whether they're going to be needed for the end problem you're trying to solve. Note, however, that this will only affect average case runtimes, as there could be certain inputs that would require the whole state space to be visited. So the worst case runtimes generally won't improve, even for problems where this is a very effective optimization. So as you can see, there's some pros and cons to each approach. But the reliance on hash maps for the top-down approach and the impact that this has on worst-case runtimes will often preclude its use in algorithm subjects. Thanks for watching my video. Hope you learned something.
Thank you so much, sir. So, there's no need, I think, to watch the other one. Is gonna talk the same thing. Let's skip it and let's jump to the let's code. Now we have idea about bottom to top and top to bottom And let's see how we're gonna do it. Let me share the full screen. Okay. Okay. First, let's read the problem. So we have climbing stairs. You're climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? Wait. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? Okay, so you're climbing staircase. It takes n steps to reach the top. Okay, so we have a staircase. What? 2? Its output is 2. Explanation: there are 2 ways to climb to the top. 1 step plus 1 step, or 2 steps in one time. Okay, so there is this way, there is this way. So how many ways we have? 2. Input, we have three problems. Sorry, 3 steps, and we have 3 solutions for it. Like 3 solutions to climb. There are 3 ways to climb to the top. So step 1, 1 step, 1 step, 1 step, 2 step, 2 step, 1 step. Okay, interesting. How we can do this with dynamic program. So let's go first. Take our problem to Excalibur as always, and let's see if we can solve it. I believe we can. And if we couldn't, it's okay. We can like watch a video solution about it and learn from it. So first, let's say we have 2 steps. Let's use this tree first because it have more solution. So 1 step, 2 step, video is bigger, 1 step, 2 step, 3 step. So now we have 3 ways. We're gonna let's say this is us, lots of hair, and I jump 1 step, 1 step, 1 step. This is way. The other way is 1 step, 2 step, 1 step, 2 step. The other one, 2 step, 1 step. Okay. Okay. For example, how we can do this with the top to bottom or bottom to top. So top to bottom is gonna be recursion. Maybe we do it simply with bottom to top, bottom to top. So if we set bottom, which mean here it's gonna be 3. So we need to find 3. This is the bottom to top. So bottom to top. Okay, let's do it like this. We have bottom to top, right? We can do, let's do it like a tree. So first we have n3. 3. Now I'm gonna add
subtract
0. So I'm here 0.
Start with a tree to see what it looks like.
Then I have 2 choices. I have +1, +2. So +1 is gonna give me 1. +2 it's gonna give me 2. Then here I have 2 choices. two choice. I have 1 plus 1, it's gonna give me 2, plus 2 is giving me 3, and 2 is gonna give me 3, and 2 plus 2, 4. So I can see here that I found solution I'm looking for here, but
Still,
I can
one situation like
yeah, this one.
we add.
With this one we didn't
Yes.
finish, so this one is gonna be 2 plus 1, 3, 2 plus 2, 4. So this one is 4 is bigger than 3, so we can stop here. 4 bigger than 3, we can stop here. Now we have 3 here. Now we can see that we found 3 times. So does that mean we return 3?
Absolutely.
Okay, now we can see something here. We have we processed 2 here and we processed here. But I think so if we're working top to down, or like top to bottom, top down, we're gonna process only 1, because we're gonna have like hash table. So this not gonna be processed, and we're gonna process 0, 1, 2, 3. 0, 1, 2.
I don't think it's
0, 1, 2.
I don't think it's not that it's going to be processed. It's just that we already have the value of it.
Yes. It's gonna be
So
processed, but we're gonna skip the calculation and we're gonna go take it directly from hashmap and then return it.
Okay.
So it's gonna access, like we're gonna call. No, we're not gonna call. So when 0 gonna call 2, it's gonna check here. Is 2 exist? Oh, it exists. Okay, I'm not gonna call it. Okay, what's 2 supposed to return? It's supposed to return, let's say 5. It's gonna take this value from the hash map. Okay, we are understand this more clearly. Now, how we can turn this to code? Think with me. Think.
We just use recursion, then put a hash table.
But we want to do it bottom to top. So bottom is 3. So I'm trying to remember what he did in that video, how he turned it to code.
So I think it's more like you have 2 values, or yes, 2 values, and then you are checking for the how do you put it now? You are checking from the solution, or you are checking from the solution, you are checking back, or checking from bottom up. That's, you are checking from the solution, and then you are adding up to the solution.
So we are checking from 3?
Yes, so you are checking from 3. And then you are the same way he did in the Fibonacci sequence. For that one, he was checking from 5. So he already had 0 and 1. So what he's doing next will be adding those values to adding. So you're only taking 2 values and adding them together until you get the value you are looking for, or until you get to the point you are looking for. That's n equals 5.
Okay, maybe I give you maybe I share with you link, and you can like maybe demonstrate in the. What you think?
Okay.
It can be better like to follow with you. We can copy link. Okay, here is it. The chat. Does this work?
Please, before then, just help me explain this tree that you just.
Okay, the canvas is too big. Okay, maybe I should save it or something. Okay, it's working. Oh, someone asked something. Can you repeat that? Hello?
Okay, please help explain this tree that you just formed, the thought process about it.
Tree. Okay, so here we are here, right? In step 0. There's step 1, there's step 2, there's step 3, right? Right? You with me? Ini? Hello?
Yes, I'm with you.
Okay, so we're in step 0. How many choice we have to do from step 0? We have 2 choices. Okay, this is gonna annoy us. Can I do this? Okay, there's still something. Okay. So I can't click. Okay, never mind. How I can solve this problem? Let me create a new Excalibur. New. How to do new? Can I just delete everything? Okay, I guess if I copy this and I select everything and delete it, then paste this. Okay, hope that message go away. Okay, we said, so we are in 0. How many choice I have? I have either do +1, +2. If I did +1, I am in 1. Oh. Okay, maybe the problem is coming from sharing. Okay, so 1 and 2. So far you understand this, right? Right?
Yes.
So basically, if we're in step 0, how much step is going to take us to get to 3? And so basically we're checking all the choices we can make and which one gonna land us to 3. So we follow this path, it land us to 3, follow this path, land us to 3, this path also land us to 3. So because the question, it said like how many distinct way can you climb to the top? So we need to find them all, 3 of them. So we did find them. So if we can calculate the number of this, how many, we can find the return.
Okay.
Now to do it with the bottom to top, okay, this is annoying. Error couldn't save the back and database. The canvas seemed too big. You should save the file locally to ensure you don't lose your. Okay, bro.
I think this page you drawing in is the it have a lot of drawing.
Okay.
You can create a new one.
I will save it in local.
All right. Create a new one and paste this.
Okay, how I can create a new one? Just okay, 1 second. Think my Chrome did freeze. I think this Excalibur from the beginning of Alex. Okay, I save it in local. Let's see if it did still show the error. I'm gonna create new one. So now bottom to top is we're gonna start from here So we're not gonna use recursion. Now, how to do it? I think someone did explain. Okay, never mind. Let's do Excalibur. But when I do Excalibur, it just take me to this. How we can do? Maybe I remove cookies. Any idea? Okay, remove this. Okay, we have new. Let me copy that. Oops. Oh no. It's okay, we can I copy this before it go away? Okay, we're safe. Reload this by, okay, reload it. Leave. Thank you. Okay, so how we can calculate from the bottom to top to find that we have 3 of 3. How we can do that? Any idea? Brainstorm with me. If we stuck, we couldn't think of solution, we can watch a video about.
The first one is when you go in the right, 0, 2, and 3. Second one is 0, 1, 3. You add 2 to 1. It's like it's three answers.
Like this, or like this?
No, and the tree. If you see the tree, the tree you draw.
Okay, this one.
You see 0, 2,
0,
3.
Okay.
2,
0, 2, 3.
This is the first one. The second one is 0, 1, 3.
The second one is 0, 1, 3.
3. The third one is 0, 1, 2, 3.
Okay, so 0, 2, 3, 0, 1, 3, 0, 1, 2, 3. I can't see it, to be honest. If someone see it, like if we wanna put it in array, how it can work? Like we did with Fibonacci, can we do that like that?
Mansif?
Yes, please go ahead.
Yeah, maybe let's first figure out the base case. I think
this one.
No, the base case are the first step 1 is 1 and step 2 is 2, and then
step 1 is 1 and step 2 is 2.
Yeah. So to go to step 2, we have 2 options, which is 1 plus 1 and 2.
1 plus 1.
In the tree, he means in the tree.
Okay, yeah.
The tree you have
1 plus 1.
And 1 plus 1 and 1 plus 2. In
this 1 plus 2. Yes.
1. No, in the child of 1. Child of 1.
Okay, we're gonna continue. 1
yes,
plus
1 plus 1 and 1 plus 2. In the other side. Other side of 1.
This 1 plus 2. Okay, yes. Plus 1 plus 1 plus 2.
Okay.
Also.
Okay. Go on.
Yeah. What else?
Do it with 2.
Yeah.
Do it with 2.
Okay, plus 2 here. Then plus 1 plus 2. But is this recursive?
Are we working?
Yeah, like bottom to top. But if you guys want to do it recursive, we can try.
No, it's not recursive. It's let's do from bottom to top in iterative way. So I'm just brainstorming how,
Yeah.
how we can do the steps.
Okay.
So yeah, I think the base case in this question are
Okay, so base case, let's say 1, 2,
1
right?
and 2.
1, 2. And 0, 1, 2, 3. So if you remember, he did n plus 1, right? So, okay. So n, in our case, n is 3. 3 plus 1 is 4. 4, that's mean this is 4, right? We create area of 4 space. And we have base case of 1, 2.
2, yeah.
Now, here, what will be the equation? Or like, okay, yeah, continue. Tell me your thought process.
Okay, so from the question, to go to 3 steps, you have 3 ways, which is 1, 1, 1.
Oh, wait a second. We start from 0. Isn't it should be 0, 1, 2? 0, 1, 2. I'm not sure. Maybe I'm confusing stuff.
Can you forget the 0?
Okay, let's keep going with 1, 2. What we gonna do?
So go to move 3 steps. We have 3 ways, which is 1, 1, 1, 1 and 2, and 2 and 1.
Okay, you lost me.
I lost myself too.
It's okay, we are trying. This is good. I'm sure someone is thinking with us. So this is base case.
Is it not 0, 1, 2?
I think 0, 1, 2 is the base case because we start from 0. Then, because if you notice here, we have 0. And this step we're gonna always do it. So 1.
Let's try looking at it from a recursive perspective to get the base case.
Okay, that's a good idea.
If we're doing recursion, what we're looking for is we don't want to go beyond. So if we're going back up, we don't want to go beyond 0. So the base case will be 0. That's based on our tree. The base case will be 0. So what we're now doing now is to find how many times do I have to climb the stairs by using 1. So I add 1 to my base case, and I'm on the first step. I add 1 again. That's doing the right side. Then doing the left side, we're adding 2. So using 0 be our base case. So we have 0 as the first element of the array. Then we're now doing add 1, add 2 for the next element.
Okay, I think I did confuse you guys because like in the video we did watch, when we go to bottom up we don't see this. I think this is something we see only in recursion. So because we are not working with recursion, so this is what should we be the focus. So we're gonna start in 0, gonna start 1, 2, 3. Somehow we need to find this 3. Now what will be if n was equal 3 and I do an array of n plus 1, it's giving me this array that have 0. So it's gonna be first
I think we have to use top down because we have to begin with 0 to the 3. Know what I mean?
I mean the problem, you can solve it with bottom to top or top to down. You are free how to do it, but we want to do it with bottom to up. So this is the result of our when the bottom to up finish, and we start array empty, right? Maybe we put something here, which is 0, because we are in 0, right? I think we always start from 0. Now, why this should be 1? If we think about it.
Okay, why I think we can even append 1 to it, because we can have a case to check if n is equal to 1. We know that there's only one way to climb a one. We can just append 1 to it and start thinking from 2.
Okay, so we are starting from the bottom. That means we are here. So like to reach from... So this here is 0, 1. So this is 0 because we are in this step. Now, if we go to this step, to reach the goal, to reach this goal, we need 1 step. That's why it is 1. Now, if we reach this step right here, how many time to reach the goal? It's gonna be 1, 2. So it is 2. If we move this loop here to 0, it's gonna how many to 1? Sorry, to 1. How many should be to reach to the goal? 1,
it's
2, 3.
2 or
so it gives us 3. So I guess this is the algorithm. I will repeat it. So we were a bit confused, or I was a bit confused, because it's a bottom to the top, right? And the bottom is what is the goal, the at the top here. Now to reach the goal, our goal is 3. It's gonna be 0, right? Because we are here. So when I'm gonna loop again, right here, 2. So this gonna be 0. I'm gonna loop. I am in this step right here. To reach the goal, it's gonna be
1.
1.
Yes.
1. Okay, so maybe if we start this with 1, I can do n minus 1, n plus 1, n minus 1, because this value, I'm gonna add it to here. So this gonna be 1. Oh, wait, how we can do this? Yeah, it's same. 1, n minus 1 plus.
We have to give the value in default, like the index of 1. He should have 1. Index of 2 should have 2.
Okay, we add it to the index. Is that what you're saying? Okay, there is an idea in my mind, but I lost because I did watch. I think yesterday or 2 days ago, something like this. Yes.
Please, can you remove this thing you have on that step? The stage. Just remove the arrows you have there. Let's do a little algorithm here.
Is there a way to?
Okay. So let's start from the first step. That is 0. We're starting from bottom to top. So we start from 0. That would be we are starting from bottom to top.
So this here.
Yeah. Yes. So if n is equal to 1, we would return 1 because it only takes you cannot climb 2 steps at a time when we just only have 1 step. You can only climb 1 step at a time, and that's the only way you can climb if n is equal to 1.
Mhm.
So if n is equal to 1, we can
If
return 1. M equal to 1.
okay, so this is a Python style. If n equal to 1,
Yes,
sorry, pseudocode, not Python style.
that's really
Return
so
1.
much.
I'm like,
Yeah.
what? Did they say Python style? Okay, what else?
Yeah. So now we are going to start. Now we are going to get into the main code. That is, if n is not equal to 1, we are going to append 1. That means we have already climbed 1 step, and we are going to start from 2.
Okay,
It's just
so
going to be
else, if it doesn't equal to 1, we're gonna what?
we are going to
No, you can just
yeah, we don't
condition
really
of
need
n equal to.
Okay, if n equal to.
no. We don't need to check if it is equal to 2. That is from 2 above, we can continue. So we are going to take a loop.
Okay, so if n, do I do else?
That one.
No, you don't need an else. As long as we have returned, that's the return statement. You don't need
Okay,
an else.
so for loop.
Yes.
Okay, for loop.
So we are going to loop from range. We are going to loop from range.
Range.
N,
So
yes.
E or what? N? N in range.
Yes, we can loop from yes. N in range. We can start from 2. We can start sliding from 2 to N. Start from 2
N.
N. Yes. If we start from 2 to N, that means we must have appended 1. You will append 1 to a list. We are going to keep track of this, and we append 1 to that list.
Okay, so list append.
No, we might have appended before the loop. Why I'm saying so is that we are going to use it to calculate and append 0 and 1 to that.
You can call
Okay,
that
so list
business.
0, it's gonna have 1. That's
No,
what
like
you mean?
list. No. What I mean by we can append 0 to, we can make a list, append 0 and append 1 to it, so that we are going to use that.
Okay, here's the list.
Yes.
Okay, and we're gonna append them to index 0, right?
0, yes, append 0 to the first.
So 0 or 1?
We are going to append 0, then we are going to also append 1. So we are going to have 2 items.
Okay, and the index 1 is gonna be 1.
Yes, it's going to be 1.
Okay, what else? Wait, where is it?
Okay.
Oops. Okay, it's away. Okay,
Okay, so please, inside the loop, we are going to. Okay.
I still don't get your idea, but let's keep trying.
Inside the loop, we are going to append to the n index. While we are looping, the n index now is going to be 2. Since we are going from 2, the n index is going to be 2. So we are going to append at n index. We are going to append list index n minus 1 and index n minus 2. It's just going to be the same thing the same thing we went through, because I realized that same pattern is giving us this trade at the end of the day. Yes.
Okay.
minus 2. You are doing I. We're using n.
N minus 2. Okay.
So by the time we finish this loop,
We're gonna
the last
return. Oh, we're gonna return list in.
yes.
Oh, okay. So it is the same code.
So that's what I realized from this pattern here. What I don't know is that if the index is really going to work, because at the end of the day we have 4 items here, so we are going to go from range n, from range 2 to n plus 1, since we are having like 4 items here in the list already. You get what I'm saying? So if we try this, if it doesn't work, if we have an index error, then we are going to go from range 2 to n plus 1.
One second.
I'm saying that if we in the for loop, because we have,
I
so
think
that
this
would mean
n should be
plus 1.
plus 1 because the array should be because we start from 0, right?
Yes.
So plus 1. We can try it. Let's see if it's gonna work on this. So it should return 3, right? If it work on this. Okay, let's do a simulation. We create a list, we put 0 and we put 1. Now we loop from here. So this list should be n. It doesn't matter because we're appending. Oh, we're not appending. So this list should be okay. Why not just append then? Just append this list, append.
Okay.
So we create a list, like we don't care the size, so we're just gonna append this. So it's gonna be, what's the value here? It's supposed to be 2, but let's see, n minus 1. N is index. Let's do e so we don't get confused. E.
Yeah.
Return n. Okay, we are n is the parameter of the function.
Yes.
So 0 1 here it's gonna be list e minus 1, e minus 1, e here minus 1 is this. The value of it is 1. So 1 plus what? Plus e minus 2, which is 0 plus 0. So it's gonna be 1. So maybe this should be 1 by default. So maybe here instead of 0, 1.
Okay.
So this way, let's see if it's gonna work. 1. This way is gonna be 2 because this one is gonna be 1. Now let's go to the next loop. We did loop again. This one go here. Sorry, what I'm doing. This one was here. Oh yeah. Wait, 2? I think 1. I think it should be 1. Okay, let's repeat simulation. I think I confused myself, confused you guys with me. Okay, let's not care about the size of this area. Okay, let's say we can have many as we want. Now, okay, we start. E, it's gonna be on 2. So this is 0, this is 1, 2, 3, 4, 5. Now it's here. It's gonna append 1 plus 1, so 2, right?
Yeah.
Then it's gonna loop. It's gonna go to 3. It's gonna append this value plus this value, which is 3.
Yeah.
So wait, isn't this Fibonacci?
It's yes, I already say that.
Okay, so it's working. It is Fibonacci just with stairs case. Okay, you wanna try it, guys? See if it's the list code gonna accept it. We can just copy the same thing here. And let's see. List. I think we shouldn't call it lists. I'm gonna say results. Results.
Append. Result upon append.
Yeah. Run. Zero.
Out of range.
Oh, it's
because you have
okay.
to specify the
yeah. So
how much
just do one here. Oh, just do one. Just do one. Okay, run. Ooh, submit. Hey, let's go. Come on, it's accepted, guys. We are now dynamic developers, dynamic programmers. Good job, guys. Nice work. Let's clap.
I have
clap.
I have better runtime.
Really?
Because you can do thing better than append. You can do like the result index is e because you use e in range. You can do raise of index e equal raise of e minus 1 plus raise of e minus 2.
I see.
Do it in the code.
Okay.
Instead of append,
wait, maybe send me your code.
Equal.
It will be better.
No, you can just change
wait,
the
do
append.
I change what? Append.
Append, yes. Do
so
equal.
I will do equal. Oh, you mean the append is taken?
Yes.
Okay, so
equal raise of index e.
Okay. E.
Exactly.
So it's gonna be wait, just this result, this plus this.
Yes.
But in this case,
try to run it.
Is this gonna run like because this array is limited, so it can't append it. So
you can do. I did like the make in Go. I did it in Python. It's like this. You do is equal.
I think the array to size n.
0. N plus 1. I did like this. It means give the result the 0 all of
right
the.
now, I think.
Right.
So make times.
Okay, what if we did 1?
No, let's just keep 0. No, let's
but
keep it to 0.
No. It should have 0 because 0 in all the cases. It's like make in Go.
Yeah. Okay, so then I have to do this 0 1
yes.
1. I guess can I do this?
Yes. It's correct.
Okay, run.
No, you have to. I think do the comma 1. After 1, do comma. Yes. No, add.
Is it tuple?
Add. No, add 2. 1, 2. 1, 2.
Okay,
2, not 1. I
thought you can add them once. Ooh.
Oh yes. Submit.
Wait, can you do this? Like 1?
Wow, 80%.
Yes. I guess yes.
Okay, wait. 80%. What was the last one? What? 90%? Okay, go back please to the other.
No, you have to. I handle the case of n equal 2. Wait, I'll send you my code.
Okay, let's submit this, and we go to sleep. Okay.
This is my code. I send it in the chat.
Okay, 2. I see what you mean. Okay, guys.
You can see the runtime.
We can end it here. I think we now have an idea what is dynamic programming. It's kinda not scary as it was before, We know there is two main types, top down and bottom up. So let's hope we practice this with time. We still have a lot of time to practice, so don't worry if we don't understand them well. We still have 12 week, so we're still in week 4. We're gonna keep practicing until the end of 3 months. We're gonna be better in this. So next PLD is Saturday. It's gonna be about binary, and Sunday it's gonna be about math and geometry. Thank you guys. Have a good night. I love you all.
Thank you.
Thank you so much.
Bye.
Bye.